Lecture 51, Hypotheses Statements Revisited. I say here, the big thing here is the null hypothesis can actually contain inequality. It can be stated such that it contains inequality. All along, I've emphasized, how the null hypothesis is the one that contains equality. And I made a point of saying it contains equality. We always showed it as being equality, but really what I'm emphasizing here is it's the one that contains equality. It's the alternative hypothesis that has a strict inequality. But the null can express a non-strict inequality. That is, an inequality that contains equality. So instead of, and then I give the three examples there of a right-tailed test where the alternative hypothesis, as mu is greater than mu naught, left mu less than mu naught, or two-tailed mu not equal to mu naught. In each case, the null is that mu equals mu naught. Well, now what we're going to say is that, look below, if the alternative is mu is greater than mu naught, what we're really saying is that the original null hypothesis we could write as mu less than or equal. That symbol means less than or equal to, right? That's less than or equal. So the null hypothesis could be mu less than or equal to mu naught, in which case the alternative would be mu greater than mu naught. Or it could be, looking in that box there, the null was mu is greater than or equal to mu naught. The alternative is then mu less than mu naught. In the case of where the alternative is that mu simply does not equal mu naught, there we still have the null being mu equal to mu naught, all right? Now, not claiming that it could possibly be greater than or less than. All right, but it still contains an equality, the null. Though we've been formulating the null hypothesis the way given above at first, we've been forming it that way, that's probably the more popular way that it's done. It's generally the way it's done in research papers. But the second way is a little more intuitive, I think. And I point out here, if your if the alternative is mu, say, greater than mu naught, well, you kind of think the null should be the opposite of that, which is not simply equal to mu naught, but it includes the possibility of being less than or equal to mu naught, right? It kind of makes sense that if that's your alternative, that should be your null. If that's your alternative, then it sort of makes sense that your alternative should be your null should be the exact opposite of that. So it should contain the inequality greater, but it still contains equality in each case. The null is the one that contains equality. You must keep that in mind. All right, so let's look at an example just briefly here. I say to help you grasp this, a lot of smudge. To help you grasp this, think of the tomato plant yield example. All right, we were seeing if we could increase the yield from 12 pounds per plant, right? So the null hypothesis, so before, I guess, and let me give you the space there, forget the before. What I say is, in the previous case, we had that we were trying to see if the yield would be increased above 12 pounds. So the null hypothesis, which you want to write in that space, is that the null hypothesis is that mu is greater than 12. That's the same as it was before. All right? But now the null hypothesis is that, in fact, after we applied the fertilizer, the mu may be less than or equal to 12. So what we're saying is, we're saying that perhaps applying the fertilizer made things worse, right? It didn't increase the yield, and in fact, potentially the yield didn't even stay the same that it was before. Remember, originally it was 12. We applied the fertilizer. Hey, we're hoping we'll get bigger than 12 is the mean. Perhaps we'll actually get less. So we're including that as a possibility, right? And I say here, let's write this. Keep in mind, the null will always contain equality. All right? It contains the possibility of equality right there, right? That will always be true it just might also contain an inequality. It might also be stated such that it also contains an inequality. All right. We say that the inequality is non-strict because it allows for the possibility of equality. Right? We say it contains a non-strict inequality. All right. So then that's in that second space there. And then below that I have an example. Example, I say the mean age of all jury students is 24 years or less. All right. Now the or less makes you think, oh, we're talking about an inequality, right? So your mind might jump to the alternative hypothesis. But look, it says the mean age is 24 or less. Another way to say it would be is at most 24. That includes the possibility of equality. So what we have down below at the bottom, you have the null hypothesis is that mu is less than or equal to 24. And the alternative hypothesis then is mu that is greater than 24. Right. Okay, going to the next page, we kind of push this example a little farther. And so suppose that, so what are we doing? We are going to take a sample of jury students, compute their ages, find the sample mean for their age, find the sample standard deviation, and compute the test statistic. And we have some significance, or we're going to rely on our p-value, whatever, to determine whether we should reject or fail to reject. And also we go through and do all that like we've been doing now many times. And suppose this is what we find. Suppose we find, okay, so remember I can graph the I can graph x bar and its probability curve and transform it into the t-score and look at the t-score. And generally we were looking at the t-score, the t-curve, and looking at whether the t-score of this sample mean was out far enough to reject or not, right? But we can also look at just whether the sample mean itself is out far enough on its curve, right? And that's just the picture I'm going to draw here. So you may get this. May get this result. Testing this right here. Maybe you'll get, don't want to put a vertical bar. So we have our 24 here, and we have our curve like this. Now maybe what we get is for x bar, the alternative hypothesis is mu greater than 24. So I'm thinking, hey, if x bar is out here far enough, I'm going to reject the null and believe the alternative. Well, it could happen that x bar is actually like right here, right? If the rejection region is out here, let's just say this is rejection region. This is our critical value, whatever it is, and out here is the rejection region. Well, look, I did not only not get out there far enough, I was back here, but I was back here so much that I was actually on the other side of the mean, right? Which we don't expect to get in a test like this. We're expecting, essentially, the way things have been set up before, we're expecting here the sample mean should maybe suggest that the alternative hypothesis is true. The sample mean should be over here somewhere. And if it's over here far enough, we do reject that and believe that. If it's not over here far enough, we fail to reject that, right? But in this case, it ended up maybe over there. So in this case, definitely don't reject the null. Definitely fail to reject. I should say fail to reject, right? That's the language we've been using all along. Fail to reject. Don't is okay, but I'm going to keep our language consistent. You definitely want it because it's way far away from the rejection region. Okay. What I say here is generally the modern approach is to write the null without an inequality. So don't put the inequality and just say equal to. all right? And so just write it with the equality. If you get a sample mean on the other side of the equality, like this one is, that could indicate something. And you see here that you can see why it's not really that important to keep the less than in there, because clearly it's in the fail to reject region if it lands over here. So you don't even worry about it. The real issue is if it lands on this side. Did it land far enough out that you want to reject the null or not? If it lands over there, of course not, right? But I do say a couple of things here. I say that if you get a sample mean on the other side of equality, that might indicate, I think I had these numbered, yeah, 1, maybe bad data. Possibly 1, what we call an outlier, that is incorrectly measured, that is reported incorrect, may throw things off. All right. So, for example, you have a sample of students, and maybe one of the students' age is 20, right? You type that in, and your finger misses the 2, and you only type the 0, and so their age is 0. And that's going to throw things off probably quite a bit, right? So, of course, that sort of thing can happen. And that's why it is important that you check your data. You go over the data you've collected, you go over how you've entered it, and all of that, right? So that sort of thing can happen. It could just be you goofed, and it really should have probably been over here somewhere. Also, you could have, I say here, an ill-conceived test. Okay, and I just basically mean there something's gone wrong somewhere. I mean, this is an example of something that could go wrong. Maybe things are set up such that you're not measuring the right thing or something like that. Perhaps setup is wrong. That's all I really want to say here. Okay, it can indicate that there's genuine error. But the other thing that could happen, and I didn't number it, but the other thing is that, or test is good, test is proper, data are good. And so the effect is generally, you think of it, it's opposite of what you expect. You know, for example, do I have room here? Yeah, for example, think if you were testing a diet. You want to see, is there a mean weight loss, right? So the null hypothesis would be, you think of it as, well, okay, mu is equal to 0, no weight loss, right? And then the alternative would be mu is less than 0 if we think of a weight loss as being negative. We'd want someone to weigh negative 5 pounds or negative 50 pounds, right? Different from what they weigh, a drop in weight. But it's possible, if we do this new formulation, then the null hypothesis would be that mu is greater than or equal to 0 pounds. And if you end up getting a test statistic that throws you on that other side of the inequality in the null hypothesis, it could mean that, in fact, the diet does exactly the opposite of what you want. It could be an indication that you actually gain weight. So in other words, for an example, maybe the diet, far from making you lose weight, the diet actually maybe makes people gain weight. All right, so then what you want to do is, you probably don't want to do that diet, right? But you probably want to reframe the whole test and go back and do it again. And your null hypothesis now is that that mu, the change is equal to 0, but your alternative would be that mu is greater than 0, right? Because now you think, oh, I think this actually makes me gain weight. Let me redo the test and see if my sample mean is so far bigger than 0 that it would be in the rejection region in a revamped test. So that kind of ties in with the idea that it's an ill-conceived test. The setup might be correct, but the effect might be the exact opposite of what you're expecting, which means you probably should have switched your test around and not tested whether the diet makes you lose weight as the alternative, but tested whether it makes you gain weight as the alternative, right? So that can happen. And typically, It might be that it's not even worth doing. It's like, run away from this thing. We don't care about this diet. It looks bad. But then it becomes an interesting question. Does it actually make you gain weight? So you change that around, and your null could still be mu equals 0, and your alternative would be mu greater than 0. And then the question is it enough greater than 0? Is your test statistic far enough out that, you would conclude that it makes you gain weight? And we'll stop here.